Hello students, welcome back. Previously we completed up to section 3. Now let's resume from section 4, Euler Totient function. Given a positive integer n, we define the Euler Totient function phi of n as the number of positive integers not exceeding n that are relatively prime to n, like this, in the symbolic expression using the cardinality notation, which looks just like the absolute value sign, except that inside is a set. Or like this, using the number of elements notation, which is used for finite sets only. I've never seen anybody using this notation for infinite sets. Both are widely accepted, but I like this one a little bit better because I can use it for any kind of set, whether it's finite or infinite. In any case, that's a definition. And using this definition, we can easily calculate phi of n for relatively small n value. For example, if I want phi of 10, what do? List all the positive integers, 1 through 10, and simply count. How many are relatively prime to 10? 1 is relatively prime to everything, so that counts. 2, no, that's not relatively prime to 10, so 2 is out. 3, yes. 4, no. 5, no. 6, no. 7, yes. 8, no. And 9, yes. 10, of course not. So this is 4. And you can use computer algebra system to find out easily using the internal expression, internal function. And then please recall that we have been using this kind of computation for application like this, starting from, let's see, when did he have this for the first time? Is it lesson 9? Yeah, I think it's lesson 9. Euler's extension of Fermat's theorem. If a and m are positive integers that are relatively prime, then a to the phi of m power is congruent to 1 modulo m. Remember this? In a special case, m is prime number p, then phi of p is p minus 1, so we have the original Fermat's theorem. And this phi of m is Euler's Totient function, and we went through some examples associated to some m values that are relatively small, so that we can calculate like this. For a little bit larger m values, do you recall what we used to do in lesson 9? We used to take the prime factorization and break apart, and then break apart this into system of several moduli, and then worked out, and then combine those later. Remember those? And we could do that because this equation itself is built that way. It's a multiplication, repeated multiplication. That's one reason, but another reason, as a matter of fact, deep down is related to this. Well, the totient function is actually multiplicative. Deep down is related to that. This is going to be our first priority for this course. Oh, excuse me, not this course, sorry, this section. For this entire course, there are many priorities, of course. For this section, for section 4, this is the first priority. After that, using this, you can go ahead and set up this formula, which allow us to calculate all kind of Euler phi function. For example, if you're going to calculate something like this, Euler phi of 1,000,000, yeah, you can calculate easily with Mathematica because it can do this kind of computation easily. If you just test all the positive integers 1 through 1,000,000, it'll take enormous amount of time, even for computers. Computers don't calculate like this, it calculates like this. Yeah, of course, prime factorization will take a bit of a work, but what I gave you previously is just 1,000,000, just 6-digit number, no problem. And then prime factors are pretty simple, just 2 and 5, no problem. If you have some 100-digit numbers with all kind of expressions and numbers jumbled up, then that could be a bit of a problem, but in most cases, this will work. And of course, we have to prove it. And one of the key points for that is, of course, the multiplicative property. After all, as you can see here, the formula itself has some product expression, strongly suggesting the multiplicative property. Another thing that we have to do later in this section is this Gauss theorem on Euler Totient function right here. The summation of phi of d for every positive divisor d of n add up to any self. In other words, this summation of phi add up to the identity function. And this is Gauss theorem on Euler Totient function. And let's see. The identity function, of course, is multiplicative. And consequently, phi of d is multiplicative as well, thanks to theorem 3.5. Remember that? So you can prove the multiplicative property like that too. But of course, the problem is you have to prove this first. That's going to be your work. In any case, once you get it done, then the second identity comes really easily because this is nothing more than Möbius inversion from the first formula. So the second identity is no big deal, just Möbius inversion. In any case, there are a lot of important and difficult things that we have to do in this section. And the first obstacle is the multiplicative property. That's what we're up to, and that is our first primary goal for this section. For that, we need some preparations. Number one, Chinese remainder theorem. Yeah, there's a way to get around this, but I found it a little bit difficult to do that. I found it really hard to follow whatever written in our textbook, to tell the truth. I prefer the other method here, Chinese remainder theorem method. So let me give you a bit of a review. The moduli M1, M2, M3, and so on are pairwise relatively prime positive integers, and capital M is the product of them all. Then this system of linear modular equation has a unique solution modulo capital M. Moreover, the unique solution looks like this. A1 capital M1 mu1 plus A2 capital M2 mu2 plus A3 capital M3 mu3 plus and so on. Here, A1, A2, A3, those are obviously coming from this problem here itself, so no problem, it comes directly from the problem. Now how about this capital M's and Greek mu's? Capital M's are defined like this. Multiply all the moduli except for the kth, or multiply them all and divide by mk. Either way, you're going to get a positive integer. And because all the moduli are pairwise relatively prime, this construction tells us that mk and capital Mk are relatively prime, so that capital Mk has the multiplicative inverse, a unique multiplicative inverse mu k modulo mk. That's how you get capital Mk and mu mk. And then put all those together, you get a unique solution. That's how the Chinese remainder theorem works. Okay, that's one preparation we have to do. And here's another preparation. Some computations associated to relative prime. The first one here is something we have been using a lot. It's called Euclid lemma. A divides B times C, and A and B are relatively prime, then A must divide C. Why? A and B are relative prime, so they do not share any prime factor. So all the prime factors of A with all the powers must belong to C in order to have this divisibility. Thus comes the conclusion. That's one way to see it, but it's not the best way to prove it, because prime factorization is not a good way to prove this Euclid lemma, because Euclid lemma is used to prove the prime factorization. The fundamental theorem of algebra, the fundamental theorem of arithmetic, requires this Euclid lemma. So we have to do something else, and something else I suggest here as a sketch of proof is coming from Bezout's linear combination expression of the GCD and appropriate manipulation so that A times a certain integer is C. The detail is left to the students. How about the next one here? A divides C, B divides C, and A and B are relatively prime. Then A times B product divides C, where that too can be considered using the prime factorization because A and B do not share any prime factors. So A times B do not have any kind of overlap or anything like that. So no power just goes up. So prime factor of A part and prime factor of B part are just completely separate. So A divides C and B divides C means all the prime factors and all the powers belong to C for A and for B are translated over here. How to rewrite everything in terms of proof? Good question. You could try that, or you could do a little bit more elegant method using Bezout's linear combination expression like this, starting from ax plus by is equal to 1, and then manipulate appropriately so that ab times some integer is c. The detail is left to the students. Finally, this one. Oh, this is probably the most important of the bunch at this moment. This one here. So let's look at this a little bit more carefully. A and B times C are relatively prime if and only if A and B are relatively prime and A and C are relatively prime. The proof of the forward direction is trivially simple. We begin with Bezout's linear combination expression. A times some integer plus BC times another integer is 1. That's what this one is. And then we can just regroup. Ax times b times some integer is 1, or ax times some integer times c is 1, like this. So this way we get the first GCD, and this way we get the second GCD. Ax plus b times some integer is 1, ax plus some c times an integer is 1. Both are coming directly from here, just rearranging the order of the multiplication here. No problem. Trivially simple. Now the second direction requires a bit more work. Assume the right-hand side, so we have this linear combination expression, ax plus by is 1, and then this linear combination from the second GCD, ar plus cs is 1. And then we're going to prove this. A times some integer plus bc times another integer is 1. Let's see, how do we work it out? Let's start from the first equality and multiply c to both left-hand side and right-hand side. Why? Because I want b times c. If I started from the second equality, then I should have to multiply b so that we get bc. I started to do it here, so multiply c so that acx plus bcy is equal to c. Okay, so far so good, but look at this. Our goal is to get e equals to 1. I have only c, so I need some work. And somehow I have to utilize the second one, but this one here has the equality 1, equals to 1. Okay, alright. So take this and then put it right here. So instead of c, I put acx plus bcy, as I highlighted in red here, and then manipulate, you're going to get what you want. So we have the proof for both directions. In any case, please remember this. This is going to become important. A and b times c are relatively prime if and only if a and b are relatively prime and a and c are relatively prime. Remember that. We'll use it pretty soon.